Okay, welcome back to part 2 of the videos. So in our previous part, we learnt about wave motion as well as how the particles behave in waves. So in this part, we're going to talk about the characteristics of waves. Okay, so learning outcomes is to compare transverse and longitudinal waves as well as be able to state examples of each of them. I've already mentioned in the previous part some examples, okay, but we are going to look at them a little bit more in depth and define and use some of the terms to describe waves as well as understand how they can be found or represented through graphs. And then finally, we've got a relationship between three of these terms here, and we will learn to apply them. Okay, so you can see from this figure, even though it's just a still image, okay, there's already some possible confusion about some of the terminology of the wave. For example, in the left half, bigger. Okay, bigger is not really a very good description. Are we actually talking about the wave becoming taller, or are we talking about the wave becoming wider? Next, faster. What is actually faster? Are the particles being moved more quickly, or is the wave itself moving more quickly? So that is another example. So these are all things, okay, that we will learn how to differentiate between. So the first type of wave motion that we're going to learn about is transverse waves. So over here, you can see a little video that just shows the motion, okay, of particles inside a transverse wave. You can see that the wave is moving from left to right, okay, and at the same time, I've got some particles here marked out in red, okay, that are oscillating up and down. Okay, all the particles are moving up and down, but these red particles are there marked out to be easier to observe. And I know it might look like a bit of an optical illusion, but if I put this laser pointer here and mark out, okay, where the particle is, this red particle, you can see very clearly that the motion of the particle is purely vertical. It is not oscillating in any other direction. It's not moving left or right. It is only moving, okay, and oscillating vertically. However, okay, the wave itself is moving from left to right. So the direction of vibration or oscillation is perpendicular to the direction of wave travel. And you can see over here two examples of transverse waves, light waves, and a vibrating guitar string. So for any of you who play string instruments, okay, whether it be guitar or violin, that's the type of waves that your strings are undergoing when they are plucked or bowed or whatever way that you play the instruments. So now we got a longitudinal wave. Okay, so a longitudinal wave, the direction of vibration or oscillation is parallel to the direction of wave travel. You can see over here that the wave is traveling from left to right again, but okay, this red point marks out one of the coils of this spring, and very clearly, okay, it is moving left and right. And at the same time, while it is marking out, okay, this uh, individual coil, notice as well the coil returns back to the original position at the end of each oscillation. It does not move from left to right every single oscillation. After, okay, one oscillation, it comes back to where it started. So this motion is also periodic. And some examples of longitudinal waves are sound waves and certain waves of an earthquake. So when the ground moves, okay, during an earthquake, some of the waves are also longitudinal. So now let's define the characteristics of a wave. This is a picture, a snapshot of a transverse wave on a single rope. Okay, and let's now define these characteristics. You can see here that the displacement of any single point on the wave, okay, is this vector, because we know that displacement is a vector, okay, from the rest position to where it is. So the displacement for this point P would be from the equilibrium position all the way to where the rope actually is. Next, the amplitude. The amplitude is the maximum magnitude of the displacement, meaning it is the furthest that each particle will travel from the rest or the equilibrium position. For a transverse wave, okay, crests are the highest points and trials are the lowest points. Okay, you can see over here, in phase describes 2 points that always have the same direction or motion, or they're always in step. So for example, P and P prime here, they are in phase. Okay, they're always in the same displacement, okay, or the same height. All the crests are also in the same displacement, okay, and all the troughs are also in the same displacement as each other, so they're all in phase. Now, something to be very careful of is just because a point is at the same displacement, so where I've highlighted here, does not mean that it is in phase with other points which are at the same displacement. Because as this wave travels, P and P prime, okay, are actually going to move one way, while this point highlighted here is going to move the other way. So they must be part of that, the same part of that shape. So in this case here, it's a sine curve. Those of you who remember your maths graphs, okay, so it must be the same phase. So you might have learned things like the basic angle, or even learned about the term phase in maths. That is a visualization. This is it in action in a real life wave. And then the last term is the wavelength. So the wavelength is the shortest distance between two crests or two troughs. Okay, so this is one wavelength. It is from one part to another part, and this actually tells us the distance, okay, between the oscillations, because this one wavelength will tell us how long before the next identical segment of the wave comes along. Okay, and for those of you who are curious, this letter, this symbol here is called lambda. It's Greek. Okay, and that is the symbol for wavelength. Okay, I know there's a lot of bit information. Please feel free to pause and rewind if you need the time to do so. Okay, so the shape of the wave, that is known as the waveform or the wave profile. And again, what we mentioned about the phase, okay, 2 points on the wave, they are said to be in phase if they are the same stage in that oscillation cycle. So they're always in the same direction or motion, they're always moving in step. And every point on the wave goes through a cycle of different positions and different velocities during the course of the oscillation. So taking the moon as an example, okay, we know that the phases of the moon go through a cycle of 28 days. So this time 28 days is very useful, okay, and in fact before modern timekeeping methods, the moon was one of the ways that ancient peoples used to keep track of time, because this was something that repeated constantly, regularly. So the same thing happens for waves, okay, and sorry, let me move back here. This here is called the period of a wave. So the period is the time a wave takes to repeat back to the same cycle. Now this might sound very similar to the wavelength, okay? But remember that wavelength is a unit of length. It is the distance between two identical parts of the waveform. But period is the time duration that the wave takes before it matches itself again, or for a particle to complete one full oscillation. So even though these two things are to do with repeating, okay, one is a unit of length, one is a unit of time. So please be very careful about that. So now moving on to some of the graphs, okay? Here we have what we call a displacement distance graph. So when I have the wave on a rope, okay, on a string that is vibrating over here, and we take a snapshot at a particular instant in time, okay, what we get is a displacement distance graph. So this is like a photograph of the wave. So because this is a photograph of the wave, okay, none of these particles here and this photograph are moving. We don't actually know what direction they're moving, and in fact, we don't even know what direction the wave is moving. Okay, for that, we have to use some other information, or even just the normal common sense of knowing, okay, where is the source of the wave. But if we're just given a graph like this, okay, we won't know what direction the wave is going and what the velocities of each of the particles in the wave are, because all we have is the displacement of the particles from the rest or the equilibrium position. However, from this, we can determine, okay, here is a crest, here is a crest, here is a crest, as well as where the troughs are, here, here, and here. And as we know earlier, the wavelength lambda of the wave is the distance between each cycle of the waveform, each repeated part. So the waveform will repeat itself after one wavelength. So you can either take two crests, two troughs, or if you're more confident, okay, one cycle like this that goes up and down. Okay, so one sine wave for those of you who are more comfortable with the math terminology. So this is the displacement distance graph. And besides the wavelength, okay, this lambda, we can also find the amplitude, because the amplitude is the largest displacement. So the largest magnitude of the displacement you can be found by looking at either the crest to the equilibrium position or the trough to the equilibrium position. Either of this would give you the amplitude of the wave. Okay, a very common mistake that students make is to take this and then double it. So you take from the crest to the trough. Okay, that is not the amplitude. The amplitude is only from the equilibrium position. So please be careful about that. Next, okay, what we have is waves can also be described using displacement time graphs. So instead of taking a snapshot, like what we have here, a photo of the wave at a particular point in time, what someone can do in order to describe a wave is to look at a single particle and how it moves over a period of time. Okay, so here we have a diagram of Bob on a boat, okay, and he's in some choppy waters and the wave travels across the sea. So we are just taking Bob's vertical position here and we are tracking it over time. So at time t0, he's moving upwards because the wave is traveling from left to right. So he's going to ride up to the crest. Okay, but right now he is at equilibrium position. So at the next instant, time 1, okay, he's at the crest already, he's moved up, but he's momentarily at rest because, okay, he is changing directions from moving up to next he's going to move back down, back to the equilibrium position. So the next instant, now he moves down. So we can then plot this graph, okay, to find the displacement time graph of Bob. And you can see over here, he starts off at the equilibrium position. Then at some time, he manages to get onto the crest. And then he comes back down to the equilibrium position. It wasn't shown in our diagrams, but he would then go into the trough and then come back. And then that would repeat again. So like I said earlier about the example with the moon, okay, the time taken to repeat one cycle of motion, that is called a period. So the time taken to come back to this shape, okay, and start again, that is one period. So a very common mistake that students make is take this time only. Okay, because you think that, oh, Bob is back at the equilibrium position, that is one period. However, at this point, Bob is moving downwards. So that's not repeating the motion that he was moving upwards. Another way is you can take the difference in time, okay, between the crest. So from here back to here, okay, this gap or this duration here, that would also be the period, as would be the troughs. So it's just a little bit more challenging if you take it from the equilibrium position, because sometimes it is possible to make a mistake and find half the period instead of the full period. Now over here, we have this new term as well, the frequency. So period and frequency, these are terms that are interlinked, okay? And how are they interlinked? The period being the time, okay, that each point takes to complete one oscillation has a SI unit in seconds. However, the frequency is the number of oscillations every second. So the number, okay, of wavelengths that are generated each second, or the number of oscillations completed each second. So the SI unit of this is the hertz. The symbol for that is Hz. Okay, please capitalize the H. So you might be familiar with this if some of you have played with audio or video editing software, or you are, in the band or play any other musical instruments when you tune your instruments. So for example, what does 400 hertz mean? Okay, 400 hertz means that there are 400 oscillations happening every second. So that means that the period must be 1 over 400, because every second 400 oscillations happen. The time taken must therefore be the reciprocal of that. And that's how we get this equation, F equals to 1 over T. So the longer the period, the smaller the frequency, and vice versa. Okay, if I have something with a very short period, that means that it has a very high frequency because it repeats many, many times every second. So here there's just a quick video on the motion of particles in a transverse wave. Okay, I'm going to skip to the important part. So you saw over there, okay, that if we track one single particle, that was how it moved up and then down. And if we look, okay, at the displacement of the particle, this is how it will travel. So that is the displacement, okay, over a period of time. And then you can see over here, this would be a displacement time graph. So here you see, okay, if we follow that single particle and we say that it has a period of 12 seconds, so it takes 12 seconds for it to, okay, finish one oscillation, get back, and then restart the oscillation again. Okay, so we saw this periodic motion here. So this is showing two periods on a displacement time graph. So I'm going to show now the motion of a particle in a longitudinal wave instead. So this here shows the equilibrium positions, okay, of the air particles inside, okay, before a sound is produced. So once the tuning fork is hit, what's going to happen is the tuning fork is going to oscillate, okay, in its own type of wave as well, and in doing so, it will collide with the air particles, and therefore, okay, cause the air particles to also oscillate, and that is how sound will propagate. So here you can see, okay, because of the vibration of the tuning fork prongs, you get a series of compressions and rarefactions, and one wavelength is the distance between a compression to the next or a rarefaction to the next. And our particles here, just as we said earlier, they are going to be vibrating in a parallel direction, okay, to the direction that the sound travels from left to right. And here is an example of the compressions and rarefactions visualized using a spring or slinky. Okay, because we can't see the particles in air, using a spring will show the compressions and rarefactions much more clearly. So I'm just going to play that video, okay, to show how this occurs. Okay, so we saw that we had these compressions and rarefactions produced because the the slinky was being oscillated at one end, and then the energy is being transferred from the left side to the right side. So the same thing would happen here, okay, if we were to plot the equilibrium position and the particle's displacement, you will also get this regular oscillation, okay, and you'll be able to find from here the period of the oscillation as well. So you can see very clearly, if I only follow one particle, I'm able to find the period. If I take the entire spring but only a snapshot of it, I'm able to find the wavelength. So each graph can only help you find one of these things. Either you take a snapshot, the displacement distance graph, and you can find the wavelength, which is the distance, or you take one particle and track it over a period of time, and you find the period, which is the time it takes for it to repeat in its motion. So that's something to be very careful about, okay, not to mix up these two graphs, because very frequently they will have the same shapes. Okay, so pay attention to the units, pay attention to the names of the graph, so that you don't mix up this displacement time and displacement distance graph. Very common misconception and mistakes that students make while they are still learning about the topic of waves. So now the relationship between period, frequency, wavelength, and wave speed. So as we know, the wavelength is the shortest distance between two successive crests or two successive troughs, and the SI unit is the meter because it's the distance of length. Now the wave speed, okay, is the distance traveled by the wave every second or per unit time. So the SI unit is meters per second. So the wave speed is given by this thing called lambda over t. Why is it given by the formula lambda over t? Because, okay, lambda, the wavelength, is the distance between two points in phase. 1 over t, okay, that is the frequency, right? And that is how many times that this happens every second. So if you think about it, okay, from the Kallang wave perspective, between two successive peaks, if there are 50 meters and it takes 25 seconds for the wave to, get from one time, people stand up once and then 25 seconds later they stand up again, then it would be clear that, okay, the speed of the wave would be 50 divided by 25, because the distance between the crest would be 50 meters, and the time taken for the crest to travel, okay, from that 50 meters is 25 seconds. So that's why the formula is V equals to lambda over t. However, since we know that there is this term called frequency, which is equal to the reciprocal of the period, 1 over t, we more frequently use the formula V equals to F lambda. Okay, the velocity is given by the frequency multiplied by the wavelength. And this all works out in our units because frequency is therefore a unit of hertz, which is SI unit for 1 over second. So that means that the units are meter times 1 over second, meters per second, and we know that that is the SI unit for speed or for velocity. So here's a quick summary. Okay, we learned about transverse waves having the direction of vibration perpendicular to the direction of wave travel, and for longitudinal waves, this direction is parallel instead. We also talked about the displacement distance graph and the displacement time graphs, as well as the speed of the waves that we can deduce from these graphs.